Hello everyone. In this video we're going to discuss implicit differentiation. Now last time we did the chain rule because we could not just take a derivative as easily as we could for large powers or it just wasn't as easy as it could have been. For implicit differentiation it's because we don't have easy y equals. So if you have more than one y, or if you have a power of y, then you really can't do direct differentiation because you just don't have y equals all by itself. If we have something like the equation of a circle here, if you tried to solve for y, you would end up taking the square root of both sides, which gives you the plus minus. And that gives you two different equations for y, and you would have to find the derivative of both versions, which doesn't really work so well, and it's definitely not nice. So instead, we do something called implicit differentiation. So it ends up being that we're going to take the d dx of every term in our equation. So we would have d dx of x squared, and then d dx of y squared, and d dx of 1. Alright, so the derivative of x squared with respect to x, which is what d dx means, would be 2x times dx over dx, which is 1, but that is, and then d dx of y squared would be 2y times dy dx, and then the derivative of any constant will just be 0 times d dx over there. So you would get the d dx of every variable every time. This is significant because d dx over dx would just cancel. It goes to 1. So that's fine, dandy, and woohoo. But the dy dx would not. It stays. And 0, of course, times anything is 0. So we would get 2y dy dx equals negative 2x. Divide by 2y, both sides, and we would get negative x over y for our dy over dx. And since, as we know from our previous section, that the derivative with respect to x can be written several ways, including dy dx, then we can do the same thing. So this is just another way of finding a derivative in the best way possible to account for weird things of weird equations. So if we wanted to actually use our derivative, remember the derivative is the slope, right? The derivative is the slope. It's why we're doing it. So if we want to find the slope of the unit circle at a specific point, well, the derivative is the slope. So if our dy dx is negative x over y, and then substitute, so we get negative 1/2 over the square root of 3 halves, so that would be negative 1 over the square root of 3, the 2's would cancel, right? And then rationalize the denominator, so we would get negative square root of 3 over 3. Moral of the story being, the slope is the derivative, no matter how long or how much it takes you to get there. Okay. So, how about something a little bit more annoying. We start the same way. We have this lovely thing, and we're going to take d dx of every single term. So d dx of that, and then d dx of the 2x, and d dx of the 3y. So our right-hand part of the equation is actually pretty simple. So we got derivative of 2x, which is just 2, plus the derivative of 3y, which is 3 dy dx. But the derivative of our left side is not nearly as nice because we have the sign, but we also have that xy in the middle. So we're going to need the product rule for the multiplication, and we're also going to need the chain rule. So the 5 will come out front. So I'm just going to push that to the side for a second. And let's focus on just the inside. So let's see here. If u is xy, then the derivative would be the product rule, right? So u prime would be f prime g plus fg prime. So that would be f prime g, so f prime g plus f g prime dy dx. Yep, and then that's the product rule part. And then we also have the chain rule, because we used u substitution here. So the d dx part would be, let's see, the 5 would be out front, and then we would have the d dx of sine u times u prime. So that would be 5, derivative of sine is cosine, and then u is xy, times u prime, which is y plus x dy dx. And that's the left side. And then we have the lovely right side. So we're trying to solve for dy dx here. And we have dy dx on both sides of the equation. So just like if we were doing the same thing with, let's say, z, and we had that on both sides of the equation, in such a scenario, we would do the exact same thing for this case. So the first thing that I would do is distribute my left side. So I would have 5 cosine xy, 5y cosine xy plus 5x cosine of xy dy dx equals 2 plus 3 dy dx. And I want all my dy dx terms on the left and everything else on the right, because I'm going to use GCFs. So let's see here. That would be 5x cosine of xy dy dx minus 3 dy dx, 2 minus 5y cosine of xy. Okay, so treat dy dx as if it's a GCF and pull it out front. And at that point, we can just divide. So our dy dx would be 2 minus 5y cosine xy all over 5x cosine of xy minus 3. Be careful. The basics of implicit differentiation is just that you're taking the derivative of every term with respect to x, finding d dx of every single term. But at the same time, we also have all of the rest of the rules. The product rule, the chain rule, the quotient rule, all of those still apply. So if we have to, we can get very, very interesting results in the middle bits. So be careful. Go one step at a time and don't try to do anything in your head. So let's do one more. We want to verify that the point 1212 lies on the curve that, and then determine the equation of the tangent line. So just to verify that the point's on the curve, we would do simple substitution. So 12 cubed plus 12 cubed, does that equal 24 times 12 times 12? And yes, it does. You can verify that with your calculator if you wish, or you can just trust me. You probably should verify it with your calculator, so pause the video, go verify. Okay, so we want to determine the equation of the tangent line. So the equation for the tangent line would be y minus y1 equals mx minus x1. We know this. And then the slope would be dy dx at that point, 1212. So we actually have a lot of this known already. We just need to figure out what dy dx is. So we take the d dx of every single term. So the first one's easy. So it'd be 3x squared plus 3y squared dy dx. And then that's not so easy. So once again, we have the product rule. So 24 times f prime g plus f g prime. Alright, so that's 24y plus 24x dy dx. And there we go. So now we want to solve for dy dx. So every term that has dy dx gets moved to the left, everything else gets moved to the right, and we treat dy dx as a GCF and we'll pull it out. So dy dx, and then 3y squared minus 24x from the other side. And we got 24y minus 3x squared. And then we can divide. So dy dx, so 24y minus 3x squared over 3y squared minus 24x. Now, we can take out a 3 as a GCF everywhere and make it go away. But since the goal is actually to find the tangent line and not the derivative itself, we don't really have to. We could, but we don't really have to. But for the sake of argument, I'm going to anyway. So 24 divided by 3 is 8. So there we are. So we use the 1212 point that they gave us, and we put that into the equation. We just found the dy dx. To get the slope, use your calculator. That's what it's there for. Right? So, dy dx, 8 times 12 minus 12 squared over 12 squared minus 8 times 12, which should look really interesting, right? What is that? It's just -1. Easy enough. So, now we can use the actual formula. Y minus y1, mx minus x1. So that would be y minus 12 equals -1, x minus 12. solve for y. So we would get negative x plus 24. And there we are. So we're just adding one more possibility to what we already know. The chain rule, the product rule, the quotient rule, all of that works together and works with implicit differentiation. Don't skip any steps. That is one of the easiest ways to mess up, especially with implicit.